Hello, and welcome to a digital lecture for Salt Lake Community College. This lecture will be the second to cover Section 3.5 for Intro to Statistics, considering inference for a single proportion. Now that we demonstrated the setup for one proportion, such as the mean, standard error, how to claim the normal model is appropriate, and how to use the Geogebra to calculate values, we will focus on the applications directly related to confidence intervals. To construct a confidence interval for a proportion, you first need to make some checks for the normal model. Verify that the data comes from a random sample or randomized experiment. The observations are independent, and also verify the sample size is large enough using p hat and n. If the conditions are met, then the central limit theorem applies, and the sampling distribution of p hat is well approximated by the normal model. Construct the standard error using p hat of p and apply the general confidence interval formula. That formula being point estimate plus or minus z star times the square root of p hat times 1 minus p hat divided by n. Reminder that the z-score with an asterisk is the z-score associated with the given confidence level, covered in section 3.4. There's a small table for common confidence levels and their associated z-scores that you will see printed here in these notes later on in the lecture. But, as a reminder, the first example covered in the textbook for confidence intervals used 1.96 as a z-score for a 95% confidence interval. Note as well that we refer to the z-score times the standard error as the margin of error. You could change multiple things about a confidence interval, and we should know how those changes affect the width of the interval. If you increase the confidence level, which in turn increases the z-score value, this will increase the width of the confidence interval, since the margin of error becomes larger. For a sample proportion, if we have a value close to 0.5, this will produce a wider confidence interval than the value of p hat close to 0 or 1. This is due to the standard error having p hat times 1 minus p hat. If we have a value for p hat further away from 0.5, then either p hat or its complement, 1 minus p hat, will be closer to 0, bringing down the size of the margin of error as a whole. Lastly, increasing the sample size will decrease the width of the confidence interval. This is much easier demonstrated since we see the sample size in the standard error as a division. So if we have a larger sample size, then we will divide by a larger value, which makes the overall margin of error smaller. Here's an example with some quick alterations, and we will identify the effect they have on the confidence interval. In a random sample of 100 kindergartners, 27% could read, which resulted in 95% confidence interval from 0.183 to 0.357. If nothing else changes, how will the following intervals compare? First, if we have a 99% confidence interval, changing from the original 95% confidence interval, since we would be increasing the size of that confidence interval, we likewise will say that the interval itself will become wider. If we instead change 95% to a 90% confidence interval, that will decrease the level of confidence and therefore make the interval narrower. If we have a confidence interval using n equals 150 compared to the original sample size of 100 kindergartners, then that means we have a larger sample size, which makes the overall confidence interval narrower. Alternatively, if we have a smaller sample size of 75 compared to originally 100, that will make a wider confidence interval. Lastly, if we have the confidence interval when 42% would read, this changes the original sample proportion from 27% to 42%. This means that we will have p hat closer to 0.5, and therefore we will likewise have a wider confidence interval. If we instead change 27% to 18% could read, that will change our p hat to be further away from 0.5, and therefore a narrower interval. Next, we will have one full example of a confidence interval question, which we will demonstrate both by hand and also using Geogebra. In a survey of 1,509 high school seniors who took the SAT and completed an optional web survey between April 25th and April 30th. 830 were fairly certain that they would participate in a study abroad program in college. We will construct a 95% confidence interval for the proportion of high school seniors who took the SAT who are fairly certain that they will participate in a college study abroad program. Is this sample representative of all high school seniors in the U.S.? Well, when we check our requirements, first for the random sample randomized experiment, it doesn't exactly say random in the statement, but we can make a reasonable assumption that it was conducted randomly. Are the observations independent? We will say that the sample size less than 5% of the population. We have a sample size of 1,509 high school seniors, and there are quite a number of high school seniors who took the SAT. So, we are going to say, yeah, that is likely less than 5% of the population. And lastly, is the sample size large enough? This is where we check n times p and also n times 1 minus p and ensure that both of those are greater than 10. If we do so using the sample size of 1509 and p hat, which is 830 out of 1509, we find that both n times p and n times 1 minus p, or technically p hat in both instances, are both greater than 10. With those conditions out of the way, we can now calculate our confidence interval for the proportion p. The number of successes we have in this case is the number of high school seniors who took the SAT and are fairly certain that they will participate in a study abroad program. That's going to be 830. The n value is our sample size, which we already know is 1,509. P hat is going to be the ratio of 830 out of 1509, which is about 0.55. And the z-score here is going to be relating to the 95% confidence level indicated in the statement. If we use the table below for common critical values from the textbook, we will find that a 95% confidence level chooses a z-score of 1.96. With all of those determined, we can use the formula for confidence intervals, p hat times z-score times the square root of p hat times 1 minus p hat divided by n. Plug those values in accordingly. If we find the margin of error first, which I highly recommend, we would find 0.55 plus or minus about 0.0251, which results in a confidence interval of 0.5249 up to 0.5751. You can also calculate this same confidence interval by using Geogebra. If we go to the Geogebra probability calculator, we will select the Statistics tab, and then click on the drop-down box to select z-estimate of a proportion. Let's go to Geogebra to demonstrate how to do that. In Geogebra here, when you're in the Statistics section, there's a drop-down for a lot of different options. We want z-estimate of a proportion. And all we need to do is indicate the confidence level, which was 95% for our situation, as well as the number of successes and the sample size. Our number of successes was 830 out of a sample size of 1,509 high school seniors who took the SAT. We find here as a result, at the bottom, we have the interval itself, 0.55 plus or minus 0.0251, which we had calculated earlier, as well as the indicated lower limits and upper limits, 0.5249 and 0.5751. If we make our final interpretation statement, we have to be careful about this. We will say that there is a 95% confidence that the interval between 0.5249 and 0.5751, the interval we either calculated by hand or via Geogebra, captures the true proportion. This kind of statement should exist in all confidence interval interpretations. 95% confidence, or whatever percent confidence, that your interval captures the true proportion. Specifically in this case, the true proportion of all high school seniors who took the SAT who are fairly certain that they'll participate in a college study abroad program. If you have any further questions, please be sure to review the example videos or ask your instructor.